Hello everyone. Today our topic shall be coordination compound. So first of all, let us know what actually is a coordination compound. So coordination compounds are those compounds in which the central metal atom is surrounded by a group of ligands through coordination bond. So the central metal atom is surrounded by a ligand and they are making coordination bond. For example, we have this is a coordination compound, and out here this is the ligand, this is the metal ion. Let me just explain all of them. This part is known as coordination entity, coordination pair, or the complex part, and this part, and this is known as counter ion or ionizable part. This 6 out here is coordination number, and this is the ligand out here. So as I have told you earlier, the ligands are surrounding the metal ions and they are making coordination bond with the metal ion. So out here we have 6 ligands. These 6 ligands are making coordination bond with the metal ion, and the bond is very strong and it's very hard to break the bond. So when you dissolve a coordination compound, this entire complex out here, it doesn't change itself. Its identity remains the same when you dissolve in water. But this part, this counter ions, is the only part which is ionizable. So when you dissolve in water, let's say if I dissolve this in aqueous solution, let's say if I dissolve this compound in an aqueous solution, you will have this compound, this coordination compound, when you dissolve in an aqueous solution, this complex part, it doesn't change because the bond out here is very strong and it's very hard to break the bond out here. So their identity also remains the same. Whatever out here, its identity it is, out here when you dissolve in water, it remains the same. But only this part is ionizable. So we call it as an ionizable part or the counter ions as well. So this coordination compound, they exist in solid state as well as when dissolved in water. So this is some important points about coordination compound. So there is one more term known as double salt. So we have double salt. So what actually is a double salt? Double salts are molecular compound. They are a mixture of 2 or more salt in an equimolar proportion. So one example of double salt is more salt. We have FeSO4 SO4.6H2O. So out here we have more salt, which is an example of double salt. So out here, this double salt, when you dissolve them in an aqueous solution, let's say I'm dissolving this one in an aqueous solution. So when I dissolve this one in an aqueous solution, we have Fe2 plus, NH4 plus, and SO4, 2 minus ions. So this more salt, when you dissolve them in an aqueous solution, they break themselves into particular ions. So in this process, they even lose their identity. They exist only in solid state as well. So these are some of the points of double salt as well. So now, if I say what are the difference between a double salt and a coordination compound, I can say double salt exists in solid state, whereas coordination compound, they exist in solid state as well as when dissolved in water. Double salt, they lose their identity, whereas coordination compound, they do not completely lose their identity. Double salt, they break themselves into particular ions, whereas coordination compound, we cannot break them into particular ions. Only one part of them is ionizable. We call it as counter ions. So there were many scientists who were studying coordination compound, and out of all those scientists, there was one scientist known as Alfred Werner. So he studied and prepared many coordination compounds, studied their physical and chemical properties by doing some experiments such as precipitation reaction. So based on his studies, he even derived a postulates known as postulates of Werner coordination theory. So there are some points of his postulates which we shall be discussing now. So on his first postulates, he says that metal ions, they exhibit two types of valency. That is primary valency and secondary valency. Metal ions, they exhibit two types of valency, primary valency and secondary valency. Primary valency is also known as oxidation state of the metal ion, and secondary valency is known as coordination number. Primary valency is the oxidation state and secondary valency is the coordination number. So for example, if I take the same compound CO, NH3, 6, Cl3. If I add them in an aqueous solution, we shall have CO, NH3, 6, 3 plus 3 Cl minus ions. So you should also know that primary valency, they are ionizable, whereas secondary valency, they are not ionizable. So out here, this part is ionizable, right? We have 3 chlorines out here, and the oxidation state of the metal ions will be 3 plus, right? So the primary valency out here, we can say it is 3. And whereas the secondary valency out here is the coordination number. So what is the coordination number out here? We have 6. So primary valency is 3, secondary valency is 6. And also if I draw the structure of this compound, we shall have so out here, these dark lines are representation of coordination number. So coordination number or secondary valency are represented by a dark line. So whereas primary valency are represented by a dashed line, dotted line. So these dotted lines represent primary valency, whereas the dark lines, it represent secondary valency. Also, his second point of his postulate says that metal ions, they have a fixed secondary valency. So that is the second point of his postulates. Metal atom, they have a fixed number of secondary valency, and also his third point says that secondary valency, they tend to have a fixed structure. So we have studied many structures. We have tetrahedral, octahedral. So based on that, secondary valency, they tend to have a fixed structure. So if the coordination number is 6, we can say the structure is octahedral. If the coordination number is 4, we can say it is square planar. So as the point indicates itself, they tend to have a fixed structure, a 3D structure. So these were some of the postulates or some of the points from his postulates. So there are many terminologies which we shall be discussing now. So the first one we have coordination. Coordination entity. So the first one we have coordination entity. So if I write the same coordination compound again, so the entire element or the entire compound which is present out here. So the entire square box, whatever element is present inside the square box, this entire square box is known as coordination. Coordination entity. We even call it as coordination sphere or the complex part, right? This is the complex part because when we dissolve in water, it doesn't even break or it doesn't even separate itself. So this part is known as the complex part or the coordination entity, coordination sphere. So we have different types of complex, that is cationic complex, anionic complex and neutral complex. So the first one I can write out here, cationic complex. So we have the first cationic complex we have COCl2 NH34 plus. Second we have anionic complex. And the third we have neutral complex. So out here, these are the different types of complex. Cationic complex, out here they have a positive sign out here. Anionic complex, they contain a negative sign out here. And neutral complex, they contain no sign out here. So there is no sign. This is positive, negative, and then neutral. And then next we have ligand. So first of all, let us know what actually is a ligand. Ligands can be atom, ions, or molecule which can make coordination bond with the metal ion. Those atom, ions, or molecule which make coordination bond with the metal ions, they are known as ligand. So ligands can be positive, negative, or neutral. And also we have different types of ligands, such as the first one we have out here is monodentate ligand. So the first one we have monodentate ligands. So monodentate ligands are those ligands which make coordination bond with the metal ions using only one donor atom. So they make coordination bond with the metal ions having through one donor atom only. So an example of a monodentate ligand can be NH3. So out here nitrogen is having a lone pair. So this lone pair is going to donate to the metal ions and then he is going to make coordination bond. This ammonia is going to make coordination bond. So this is one example of monodentate ligand. The second one we have cyanide, 2 nitrogen. It can make coordination bond with the metal ions. So these are monodentate ligand. So second we have Bi-Dentate ligand. So Bi-Dentate ligands are those ligands which can make coordination bond with the metal ions using 2 donor atoms. So they will have 2 donor atoms and both the donor atom will make coordination bond with the metal ions. So one example I can give you for bidentate is, we have En out here. So En is CH2, NH2, CH2, NH2. So out here they have two donor atom, one donor atom, another donor atom. So both these donor atom will make coordination bond with the metal ions. And then third we have polydentate ligand. So polydentate ligands are those ligands which can make coordination bond with the metal ions from more than two donor atoms. So out here in polydentate, they will have more than two donor atoms. So they can have 3, they can have 4, they can have 5, they can have 6 donor atoms. So if they have 3 donor atoms, we shall call it as third dentate. If they have 4 donor atoms, tetradentate, right? So it keeps on going. So one example for third dentate ligand is CH2NH, CH2, NH2, NH2. So out here lone pair, lone pair, lone pair. So 1, 2, 3. So they are having 3 donor atoms. So one donor atom, another donor atom, third donor atom. So these 3 donor atoms, they will make coordination bond with the metal ion. So this is an example of third dentate ligand. For 6 we have EDTA as well. So these are different types of ligands. So monodentate ligand, bidentate ligand, and polydentate ligand. So next we have chelation. So those bidentate ligands which make coordination bond with the metal ions using both of its donor atoms, and they form a ring structure. It is known as chelation. So they will have 2 donor atoms. Both the donor atom will make coordination bond with the metal ions, and they will form a ring structure, and we call it as chelation. So out here I can write CH2NH, CH2NH, and out here we have metal. So out here this is En, right? Ethylene diamine. So both of them, these donor atoms, are making coordination bond with the metal ions, and they are forming a ring structure. This one we call it as chelation. And this ligand which is making coordination bond with the metal ion, we call it as chelating ligand. Chelating ligand. The ligand which is making coordination bond with the metal ion is the chelating ligand, and the entire thing itself is known as chelation. And fourth we have ambident ligand. Ambident ligand. So ambident ligands are those monodentate ligands which can make coordination bond with the metal ions from more than one side, are known as ambident ligand. So they will make coordination bond with the metal ions from more than one side. So one example is CN cyanide out here. This is making bond using nitrogen, and if I write here isocyanide, this is making bond with the carbon. So out here both of them are CN itself. CN itself. CN is cyanide, whereas NC is isocyanide. So both of them are monodentate ligand. So out here it can make bond using nitrogen, and out here it can make bond using carbon from 2 sides. And also we have NO2. Out here it is making bond using metal, and out here we have ONO. It's making bond using oxygen. So from 2 sides they can make bond. This one we call it as nitrito N, and this one we call it as nitrito O. So when it's making bond with oxygen, it is nitrito O. When it is making bond using nitrogen, it is nitrito N. So these are some examples of ambidentate ligand. And fifth we have coordination number. So coordination number is basically the number of donor ligands attached to the metal ions. These are known as coordination number. So CO, NH3, 6. If I just write this compound out here, how many ligands are here? 6, right there. And this is the donor atom. So there are 6 ligands. So this 6 is the coordination number. And also if I write another compound, let's say CO, Cl2, NH3, 4 plus. So how many ligands do we have? This is the metal ions. This is the metal ions, the ligands. These are 2 ligands. There are 4, 5, 6. So we have 6 ligands out here as well. So these are the ligands surrounding the metal ions. They are making bond with the metal ions, and the number of ligand is 6 out here. So 6 becomes the coordination number. So by this we finish some of the terminologies, and so now our next topic shall be to find the oxidation state of the central metal ion. So now we have K2PtCl4. This is platinum out here. So now we are supposed to find the oxidation state of the metal ions. So out here, this is the metal ions, this is the ligand out here, and these are the counter ions. So now this metal ion, since we are supposed to find the oxidation state of the metal ion, I will put this metal ion as X. And out here, charge of potassium. Potassium charge or the oxidation state of potassium is +1. Since there is 2 out here, so 2 into 1 becomes 2. So 2 plus platinum, we are supposed to find the oxidation state of platinum. So I'll put it as X, and chlorine. So the charge of chlorine is -1. Since there is 4 chlorine out here, 4 into -1 equals 0. So 2 plus X, 4 into -1 is -4 equals 0. So X minus 2 equals 0. We have X is equal to +2. So the oxidation state of the central metal ion platinum is +2. So it's quite easy to find the oxidation state of the metal ions. You just need to know the values of the ligand out here. So out here, chlorine is -1, potassium is +1, so we have COCl2, NH3, 4 plus. So now we shall find the oxidation state of the metal ion out here. So these metal ions, I will put it as X out here. This is the metal ion, so X. Chlorine, there are 2 chlorine out here. Charge of chlorine is -1. And then ammonia, NH3 is 0, neutral. So we have 4 into 0. So whenever there is a positive or a negative sign outside the square bracket, outside the complex out here, there's a positive sign out here, and it is +1. So whenever there is a positive or negative sign, you're supposed to write the value of the positive or the negative out after the equal to sign. So out here we have the equal to sign. So after this, we're supposed to write the value of this one out here. So this is +1. So I will just write here 1. So we have X minus 2 plus 0 equal to 1. So X minus 2 equals 1. So we have X equal to +3. So out here, the oxidation state of the metal ion out here, this metal ion cobalt, is +3. So now again, this is a cationic complex, right? Positive sign out here, cationic complex. So this is the metal ion, so I'll put it as X. Charge of chlorine is -1. En, ethylene diamine is 0. 2 into 0. Ammonia is also 0, equal to this one. After the equal to sign, we have 2. Whenever there is a charge out here after the equal to sign. So x -1 plus 0 plus 0 equals 2. So x -1 equals 2. X equal to 2 plus 1 plus 3. So again, the charge of cobalt out here is +3, or we can say the oxidation state of cobalt out here is +3. So now NiCO4. CO is carbonyl, so it's a neutral ligand, and we have CO is equal to 0. So now this is the metal ion. I'll put it as X plus 4 into 0 equals to 0. So X is equal to 0. So the charge of the, or the oxidation state of the metal ion out here is 0. So we have CrClNH35Cl2. So now this is chromium, this is the metal ion. I'll put it as X. Charge of chlorine is -1. Ammonia is 0. And so what did I say? Whenever there is a plus or minus, you're supposed to write that value after the equal to sign. But there is no charge out here. This is just chlorine. So you can write the value of chlorine before the equal to sign. Only whenever there is positive and negative, you're supposed to write the value after the equal to sign. All the rest will be before the equal to sign. So out here chlorine, there is 2 chlorine out here. 2 into -1 equals 0. So x -1 minus 2 equals 0. X -3 equals 0. X equal to +3. So out here, the charge of chromium, or the oxidation state of chromium, is +3. We have K4 K4FeCl6. So charge of potassium is +1. So 4 into 1 is 4 plus X. Cyanide Cn is -1. Charge of cyanide is -1. So 6 into -1 equals 0. So 4 plus X minus 6 equals 0. X minus 2 equals 0. X equal to +2. So again out here, the oxidation state of the metal iron is +2. So we have +2 out here for the metal ion. So Cu is the metal ion, so I'll put it as X. Bromine is -1, since there is 2 bromine. 2 into -1. Water is 0, it is a neutral ligand. Ammonia is also 0. So X -2 equals 0. X is equal to +2. So out here, the oxidation state of the metal ion is +2. So by this we finish the part 1 of the coordination compound. So in part 1 we have studied what is a coordination compound, what is a double salt. We have studied some terminologies such as coordination entity, ligand, different types of complex, cationic complex, anionic complex, neutral complex, different types of ligand, monodentate, bidentate or didentate, and polydentate, what are chelations, what are ambident ligand, and coordination number. And also we have studied to find the oxidation state of the central metal ion. So in part 2 of the coordination compound, we shall study the IUPAC nomenclature of coordination